Sometimes it vanishes and becomes, and that's the problem, and that's the motivation for a biased, volume biased ESP that I will explain. But the volume of S is a martingale, and we have a ton of theorems for it. For example, proposition, we have a sequence volume of ST is a martingale. So the expectation of volume of ST plus 1 conditioned on ST is volume of ST. This is exactly martingale. And also there is another proposition in this paper that it has connection with random walk, so we say P of x y in ST is equal to PT x and y d of x, the degree of y. So what we do usually is that we can use this to estimate the right-hand side. This is the trick that we use. So we infer what is happening in the random walk from just analyzing this evolving process. So the big picture is that we have evolving set process, but it doesn't have a coupling with random walk. It may vanish. And your random walk has a process xt, your ESP has a process st, but this may vanish. Bad. But the good one is the modified version, which is called volume biased ESP. So first of all, I should say all of these are Markov chains. Markov chain, Markov chain, Markov chain. But the good thing is that between this and this, we can define a coupling. We can define a coupling, and this is good because never vanishes. That's why it is much better than ESP. ESP has problem because it vanishes, it's bad. So the volume biased ESP is also a Markov chain. And we'll define it by describing a coupling due to Diaconis and Phil, these two guys. So there is a coupling between a volume-based ESP and the random walk XT, random walk. So we start, so the process is like this. So first we start with S0 for a single vertex, and X0 is X0. And then we update the random walk. Updating rule is that if xt is x and xt plus 1 is x prime with probability x and x prime, now with probability x and x prime. And then we update the set, so if st is s, okay? So we pick a threshold, u from, so instead of picking from 0 and 1 as we did in the previous algorithm, we just sample it from 0 and p of x prime and s. So this is one variation of that. So we pick from this, not from 0 and 1. And now the rest of things is almost the same because we pick those vertices that the probability of y and s is greater than u. And this ensures that x prime is in s prime. It grows and grows and never vanishes. So S1, S2, S3, ST. So it's an evolving process. It never vanishes. So first, for example, x1 is outside, and then x prime is outside, x prime comes inside, and it never vanishes. And it keeps adding the particles. So in volume biased evolving state process, ST, and we have x0, which has, so x0 and xt are, it goes, a random walk goes here, and we select a random vertex. So if you just sample from ST a random vertex, it is just like saying that, okay, it's like going from x0 to xt, because we can always sample from this ST. So any direction that you go is the same. And of course, the probability measure for coupling ST and XT, so ST and XT, there is a coupling between them, and the probability of XT equal to Y condition on S1 ST is 1 of Y in ST dy over volume of ST. And this is the probability measure for coupling ST and XT. And there are other interesting things about, like transition kernel in this article. Transition kernel for volume biased ESP is that, so this is volume of S prime, volume of S, K of S and S prime. So this is transition probability for ESP, but this is transition probability for volume biased ESP. So you see how they are related by this factor. And they prove the proposition that for any function and any starting set, the expected value of f of S0 ST is the expectation of volume of ST volume of S0 times f of S0 ST. So you can see it as that volume biased ESP is a Doob H transform of the ESP. And another interesting thing is that your mixing times for your lazy Markov chain, it is bounded now by your trigger, by your expansion, whatever you say. Pi of mean, which is should be at least 1 over n squared, until 4 epsilon for d of u now phi is here. So if this expansion goes down, it means that this goes up and the integral goes up. So you see how when your expansion is very low, your mixing time is high. For example, you have a click here, another click here. They are loosely related. So if expansion is very low, mixing time goes high. It means that if your vertex starts here, it tries very hard to get out of this obstacle and going from one side to the other side in order to reach all this state space. So it has a bad mixing time. So we don't want that. So expansion should be, for example, in this click, expansion is high, mixing time is very low. You can go from any edge to another. So the best possible things is your complete graph that you love, or a click, for example. And so there is a great researcher, Kavi Ravikkanen, and also a mathematician, Laszlo Lowas, in 1999. They gave an article, Faster Mixing via Average Conductance. Some interesting intuition is a tree. So this tree grows and grows and grows, and for example, if one of them in a very late layer, it goes to the first one, then it connects everything, and it's a very good, interesting example. I mean, this area of ergodic theory is very interesting. For example, there's a hypothesis that omega t eventually visits all of the state space. After some time, it reaches all of this space regardless of your initial condition. For example, if a dynamical system is chaotic, it is very sensitive to initial condition because the difference goes away. But if it is not chaotic, for example, like this, if an initial condition is different, after some times they become unique and converges to something, some united variable. And so if the hypothesis is true, then Birkhoff was the guy. Birkhoff equality in 1930 says that the limit of 1 over t, if time goes to infinity, of this f of omega of t, d of t, so it is like average along trajectory. So this is equal to f of omega p of omega d omega. And this can be seen as average over all possible states. So we obtain this average and computing this. So we get left by computing the right one, because the right-hand side is easy. In physics is easy, in everything. In mathematics, graph theory is everything, is easy. And so, for example, another ergodic application is in dynamical systems, as I said, in, for example, strange attractor, Lorentz attractor. I mean, those attractors have very interesting dynamics. So after a while, you will see that, they are like this Gaussian distribution. So it's like two Gaussian distributions that are mixed together, and so it has a probabilistic. So you can find the probability of being at any states, regardless of your initial states. For example, for this initial condition, I go there, I go here. For example, with this initial condition, I go here, I go here, I go here, I go here, After sometimes it doesn't care. It doesn't matter which initial state you were in. You just say that the probability of being at this state is this, the probability of this according to Gaussian distribution, for example. So it doesn't matter where you are, because after some time, for example, this point never happens because it is outside your probability density function. And this point never happens. So you are restricted to this area. But if any initial condition that you choose, it will go. And the same trick is like in graph theory. You have some cliques, some complicated expanders. It has very great expansion inside of them, but they are very loosely coupled to each other, very loosely, maybe one or two. And then, so a particle that starts at this vertex, it should pay a lot to go to other parts of the. It should be very lucky, and the mixing time is very high to reach the all state space, to reach here, from going from here to here. But if it's just one expander, one click, for example, one complete graph, then you can go from, because it is highly connected, so it measures the connectedness of the graph. It can go from any vertex to any other vertex very, very rapidly. So mixing time is very small, very, very small. And this is good. But in practice, you have several expanders that you should identify and see that there are some sparse connections between them. So identifying them leads to great multi-way cut algorithm. And also, like Cheyenne, you can generalize Chigger inequality to multi-way kind of generalization of Chigger inequality. And you will see that when you have a spectrum, I will talk about it in next weekend. I will talk about all articles of Cheyenne Owais Karan and James Lee, those guys in Washington University, Stanford University, and Luca as well. Luca, the president of Simon's Institute. And those theorems are very interesting because you combine all your SDP, LP relaxation technology, with your linear algebra technology, which is inside spectral graph theory. And if you combine them, you will understand what is missing. How should we, because there are infinite ways to decompose your graph. So according to some measure, you can systematically improve your expander decomposition and to achieve a better algorithm, faster algorithm. For example, Cheyenne has proved a very interesting new results, even in graph theory. And of course, it has more than 100 citations, but it should be 1,000 citations because his work is really interesting and important. And people may realize in future the importance of the work of Cheyenne Owais Karan and his great advisors like Luca Trevisan, Raghavendra, Emmanuel Abe, and James Lee, and Yuval Perez, those great advisors of Cheyenne. So Cheyenne is very, very lucky to have. I wish I could have such great advisors to understand and to develop my research in a more systematic way. So that's it for today. I hope you enjoy the beautiful part of spectral graph theory, but next weekend I will talk about